Okay, so we're going to talk about a technique called completing the square. What we do with what we use completing the square for is for quadratics that are not factorable. So if you look at this first example, we'll call it example 0. Then we can actually solve this really easily by taking the square root of both sides. So if I do this, because the whole left side of the equation is being squared, so if I take the square root of both sides, I get, on the left side of the equation, the square root of x minus 5 squared. So those two things are inverses of each other. So we get x minus 5 equals, and when you square root something in an equation, you can have a positive or a negative square root. So recall really quickly, so like the square root of 9 could be 3, but it could also be negative 3, because negative 3 squared is also equal to 9. So we have 2 square roots to each problem here. And that's how we get our 2 solutions to a quadratic equation. And then adding 5 to both sides, we get x would equal 5 plus or minus the square root of 10. So now the trick is, well, how do I take a quadratic that's in standard form and make it so that it's a perfect square? So what we have, or we're trying to take expressions that look like this: x squared plus bx plus c, and we want to turn them into x plus or minus some number squared. So that's our goal right now. So we're going to look at this kind of geometrically. So I think this is a good illustration of how the technique works, because there's just a trick to it, and once you learn the trick, then it's easy to do. So suppose we had a square, and each side of this square was x by x. So the area of this square would be x squared. And then we draw 2 rectangles on the side of our square. And each of these rectangles has a width of 1. And then this side of the rectangle would be x, because it's the same as this side over here, right? So we want to find, what do we have to add here to complete our square? So currently, we have the expression x squared plus, we have, this would be 1x, and then this would be 1x, so that's 2x. And then what's the area of this square that I added to complete the full larger square? And that would be an area of 1, because this would be 1 by 1. So if I have x squared plus 2x, I add a plus 1 to complete the square. And if we now look at, so each side of this large square would be x plus 1. So this is x plus 1 squared. Okay, so let's make our square, complete the square a little bit bigger. So now I have 2 rectangles on each side. So now in total I have x squared plus 4x. And I want to figure out, what do I have to add here to complete the whole square? Well, this would be 2 by 2, so the area is 4. And altogether we end up with x plus 2, because each side of my new larger square is x plus 2. So the whole thing can be represented as x plus 2 squared. We'll do one more, and then you might see the pattern. So 1 and 1. So now I have x plus 3 on each side, which means I have 6 total rectangles. And now the thing that I have to add is 3 on each side, which would make it a total of 9. And this equals x plus 3 squared. So you might have noticed there's a pattern here. So this number that I added here every time is half of the x term and then squared. So given some expression x squared plus bx, to complete our square, like we did in this picture here, we always add the x coefficient divided by 2 and then squared. So like 6 divided by 2 would be 3, and 3 squared would be 9. And the resulting expression always factors to, or it always equals, x plus middle coefficient divided by 2, and then all squared. So once we have that trick, and the trick works the same way if this is a minus 6x, then you have to visualize taking rectangles away. So it's easy to show the demonstration if we just do plus. And it would work the same if these were like odd numbers. Yeah, so now let's use this to solve a couple equations. So x squared minus 12x plus 7 equals 0. So I'm going to subtract 7 from both sides because the constant term doesn't help us complete the square. So now we get x squared minus 12x. And I'm going to leave a space here because I know that I'm using completing the square. By the way, this is a good thing to check first to see if it's factorable. If it's factorable, you don't have to complete the square. But there's nothing that multiplies to 7 and adds to negative 12. So that's how we know that we should use a different technique to solve it. Okay, so my middle term is 12, right? Okay. So 12 divided by 2, and the negative is not going to matter because we're squaring it. So negative 12 divided by 2 would be negative 6, but we square it and we end up with a positive. And that's going to equal 36. So that's going to equal 6 squared, which is 36. So that means I'm going to add 36, but I have to do the same thing to both sides. So I add 36 on both sides. So the left side of the equation, we know, so we added this number, b over 2 squared, so we know that it now has to equal x minus 6 squared. And on the right side of the equation, we have negative 7 plus 36, and that equals 29. And now we can solve it by square rooting both sides. So square root of the left side, square root of the right side. Don't forget your plus or minus. So x minus 6 equals plus or minus the square root of 29. So then our solutions are x equals, so we just add 6 to both sides. So 6 plus or minus the square root of 29. So we have two answers, and our answers now are irrational numbers. So this is kind of a cool math fact, is any quadratic that's not factorable, that means you're going to have two answers that are irrational. So basically like something under the square root sign that doesn't simplify to a perfect square, or you could end up with complex solutions, so complex number answers. Okay, so example 2, notice we have a 2x squared in this problem, and that completing the square pattern only works when our x squared coefficient is 1. So I'm just going to take both sides of the equation here and divide them by 2. Now I get x squared minus 10x equals 5. Notice I just leave the space here because I know that this is a completing the square problem. So I have to add 10 over 2 squared to both sides, and that's going to be 25. So on both sides, I'm going to add 25. So now I know that this whole thing is going to factor to x plus b over 2 squared. So in this case, that would be x minus 5 squared equals 30. And then just like we did in the last problem, square root both sides. And we get x minus 5 equals positive or negative square root of 30. And add 5 to both sides, so x equals 5 plus or minus the square root of 30. Okay, so notice all these quadratics have to have two solutions. So there's a plus solution and a minus solution. In these next two examples, we're going to see, so last class you learned about complex numbers. So complex numbers can also be the solutions to quadratic equations. So we're going to solve number 3 here the same way we solved 1 and 2. So I'm going to subtract the 37 from both sides, because that doesn't help me with completing the square. And I get x squared minus 6x equals negative 37. And to complete the square, I add 6 over 2 squared, so 6 over 2, it doesn't matter if it's positive or negative, so that's negative 3. But I'm also squaring it, and that means I add 9 to both sides. So plus 9 plus 9. So on the left side of the equation, we have negative 37 plus 9, so that is negative 28. And the right side of the equation we know is going to factor into x minus 3 squared. So before last class you were told you can't ever square root a negative, but now we actually know how to square root negative numbers. We just introduced the imaginary unit. So if we square root both sides, then the left side is still x minus 3. But the right side of the equation, so the square root of negative 28, we could break this down into, I'm going to work this out down here. So the square root of negative 28. So I know I can pull out an I, so that would equal I times the square root of positive 28. And square root of positive 28 we can still break down further into, so 28, so this is I times the square root of 4 times the square root of 7. And the square root of 4 is 2. So this whole thing breaks into 2I square root 7. So x minus 3 equals plus or minus 2I square root 7. And then add 3 to both sides, and we get x equals 3 plus or minus 2I square root 7. Okay, so let's do one more example with it's going to have a complex solution also. And we also have a 2x squared again. But we know we can't complete the square unless this is 1x squared, so I'm going to divide everything by 2 first. And I'm going to subtract 26 from both sides. So then I get 2x squared minus 12x equals negative 26, and divide everything by 2, and I get x squared minus 6x equals negative 13. Okay, just like the last problem, we do negative 6 over 2 squared, and that equals 9 again. Did I really make 3 examples where it equals 9? I don't know. So add 9 to both sides. And we know the left side is going to be and x minus 3 squared. And on the right side, I have negative 4. And then square root both sides. And the square root of negative 4 is 2I, because that's the square root of I, or that equals I times the square root of positive 4, which is 2. So x minus 3 equals 2I plus or minus 2I. So x equals 3 plus or minus 2i. Okay, one other thing we can use completing the square for is converting equations into vertex form. So remember, vertex form is when you have y equals a times x minus h squared plus k. So the reason we use completing the square to do this is, notice that we have a part that's squared. So in order to get something that's squared, we can use the technique of completing the square. The difference in solving an equation and converting an equation into vertex form is when we convert an equation to vertex form, that means we started with a function. So I can't like subtract something from both sides, or I can't change the values in the function unless I balance it in the right way. So if I have x squared plus 8x minus 11, so I'm going to change my f of x to y. That's easier to write. So x squared plus 8x. And I'm going to leave a space here because I'm going to complete the square. So to complete the square, I would still do 8 over 2 squared, and that equals 8 over 2 is 4, and 4 squared is 16. Right? So I add 16. I don't want to mess with the other side of the equation because that's kind of weird to look at. But if I add 16 and I subtract 16, from the same side of the equation, then I added 0, right? The total value of 16 plus 16 and minus 16 would be 0. But the reason for adding the 16 is now I can group this part together, and that's a perfect square, and that equals x plus 4 squared. And then outside the parentheses, I do negative 11 minus 16, and that's negative 27. So now I have my quadratic in vertex form. Okay, and then, so last example, now this one's a little bit weird because we have a 2x squared, and we're not allowed to divide it out. But I can factor out negative 2. So I have negative 2 times 1x squared plus 2x. And then I'm going to leave a space there, and I'm going to leave my plus 9 alone. So I factored a negative 2 out, but only from these two terms. I don't really care about the constant when I'm completing the square. So now I'm going to complete the square inside the parentheses. So I have my 2 divided by 2, and then squared would be a plus, would equal positive 1. So I add 1 here. But I have to find something to subtract here to make sure my equation stays balanced. And the 1 that I added is being multiplied by a negative 2. So really, if I were to distribute the negative 2 back, I really subtracted 2, right? Because this thing here is 1 times negative 2, which would equal negative 2. So I'm going to add a positive 2 to cancel out the negative 2 I added. So that keeps the whole value of this side of the equation the same. Now, we have negative 2 times my perfect square part becomes x plus 1 squared, and then 9 plus 2 is 11. The end.